We have considered the terminal relations of an inductor and capacitor in terms of the Laplace transformed variables. What about resistor? This is of course quite simple. If I have a resistor R carrying a current IT and the voltage across this is Vt, then straight away we know that V of t equals R times I of t at all points of time. Therefore, in terms of Laplace transforms, V of s equals R times I of s. So, in the transform diagram as well, you have an R, this is V of s, and the current is I of s. So, there is no difference between the transform diagram and the normal time domain representation of a resistor. The ratio of the time domain voltage to current is R, the ratio of the Laplace transform voltage to current is also R. So, in general, if we have an element, a general element like this, and this is I of t and this is V of t, in the transform domain, we have the Laplace transformed current indicated as the current variable and the Laplace transformed voltage as the voltage variable, and the ratio of the Laplace transform of voltage to the Laplace transform of the current, let us say with 0 initial conditions. That means we are assuming in the case of a capacitor and current, capacitor and inductor, there is no initial charge on the capacitor, there is no initial current in the inductor, 0 initial conditions. So, Laplace transform of the voltage, the Laplace transform of the current, the 0 initial conditions. If these are Vs over Ifs respectively, this ratio will be equal to R for the case of a resistor. If this box contained a resistor R, that will be Vs over Is is R. If this box represents a pure inductor, this will be Ls. And if this box represents a capacitor, it will be 1 over Cs. So, if this box, if this is X, R, if X is a resistance, if X is an inductor, and 1 over Cs if X is a capacitor. So, we can think of this as a generalized impedance of this element, either R, Ls or 1 over Cs, and this of course can be extended to a combination of the elements. Suppose there is an inductor and resistance are in series, we can say the generalized impedance is R plus Ls and so on and so forth. We can also think of this from the system point of view. Suppose I have represent this element as a system, and we have a current which is given by e to the power of st, and you want to know the output, the forced response of the system for these input conditions. This will be turn out to be, if the system happens to be a resistance, a current passing through a resistance, if this e to the power of st is the excitation to the system, and the forced response is equal to, after all, V equals Ri is the equation for a capacitor, for a resistance. V equals L di dt is the equation for an inductor. V equals 1 over C integral I dt for a capacitor. Therefore, using these three fundamental relations, if the forcing function is e to the power of st, and the voltage will be R times e to the power of st. That is the forced response of the resistance. If the system happens to be a pure inductor, the relation between the voltage and current is L times di by dt, therefore, this is Ls times e to the power of st. And if the system is a pure capacitor, the relation between the forced response of the voltage to the current. Suppose treat this as a kind of differential equation, and I is the input e to the power of st. This is 1 over cd operating on I of t. Therefore, if I of t is an exponential input, the forced response for the voltage is 1 over cs times e to the power of st. So, these generalized impedances R, Ls and 1 over Cs can also be thought of as the ratio of the forced responses of the voltage to the excitation when the excitation the current excitation when the current excitation is of the form e to the power of st. So, this is an alternate way of looking at this. So, now that we have got this, we would like to set up the transform diagram of a whole circuit or a whole network in terms of these generalized impedances. To aid us in this process, let us recapitulate what we did in the case of AC circuits under sinusoidal excitation functions. We have a general circuit that is given to you. So, instead of dealing with the I of t and V of t sinusoidal voltages and currents, we represent in the circuit diagram the impedances of the various elements j omega L, 1 over j omega C, or as the case may be. And instead of the raw currents and voltages in time domain, we represent them by means of phasors. So, the whole entire circuit diagram can be written in terms of the variables being the phasors of the respective quantities, voltage and currents, and the element values instead of being R, L and C, we write in terms of R j omega L, 1 over j omega C, the steady state impedance values. We do much the same thing in the transform diagram. What we do is we represent the circuit in the same form as we have in the time domain, except that we put down the generalized impedances of the various elements. And secondly, the variables that we are talking about are, instead of the time domain expressions, we will talk in terms of the Laplace transformed variables, the Laplace transforms of the various currents, the Laplace transforms of the various voltages. A third point which is new here is whenever the inductors carry initial currents and whenever the capacitor carry initial charges or initial voltages equivalently, then we represent those initial conditions by equivalent sources in the transform diagram. So, we can have a voltage source representing the current in an inductor, initial current in an inductor, or a current source. Similarly, we can have a voltage source representing the capacitor voltage or a current source equivalently. So, the only difference is that we have initial currents represented by additional sources, excitation sources. Otherwise, the diagram, the approach is very similar to what we do in the case of AC circuit analysis. We deal in terms of transformed variables instead of phasors. We deal with generalized impedances instead of sinusoidal steady state impedances. That is, wherever j omega occurs, we use S instead of j omega. That is the only difference. So, this will be illustrated by means of an example which we will now take up to illustrate the technique of the Laplace transform to the transient analysis of a problem using the transform diagram. Let us take an example. We have a 10 volt source operating in a circuit comprising a resistance 3 ohms, 2 ohms, 1 Henry with a switch. This is 6 ohms and the switch is closed at t equals 0 after having been kept open for a long time. S is kept open for a long time and is closed at t equals 0. So, we are asked to find out I of t find I of t for t greater than or equal to 0. Yes. So, what we need to do is set up the transform diagram for this. So, you have for the 10 volts we straight away take the Laplace transform of this. So, that becomes 10 over S, because after all it is a DC source, the transform of a constant 10 volts will be 10 upon S. The resistance 3 ohms is represented by 3 ohms again. This is 3 ohms. So, you do not have to write ohms. The generalized impedance of the resistance is 3. Now, this is 2. The resistance here is 2. As far as the inductor is concerned, its generalized impedance is S, because it is 1 Henry inductance, therefore Ls is S. But we must also have here Li0, a voltage representing the initial current in the inductor. And what is the initial current in the inductor? When the switch is kept open, 10 volts drives the current to the 3 plus 2, 5 ohms. Therefore, the current here IL0 minus is 10 divided by 3 plus 2, 5, 2 amperes. Therefore, Li0 is 2 volts 2. So, the strength of that voltage signal is L times I0 which is 2. We are substituting 0 minus values. In this case 0 minus and 0 plus are one and the same, but we are substituting 0 minus values because they come naturally to us. And then you are having a 6 ohm resistance. So, we solve this equation in terms of the loop currents. After all, once we have the transform diagram, the equations are written down in exactly the same manner as we would do for DC circuits. So, you write down the loop equations for these two loops in terms of the variables I1 of S and IFS. IFS is what we are interested in. So, the first loop you have got total impedance is 3 plus 2 plus S, 5 plus S times IFS. The mutual impedance between loops 1 and 2 is 2 plus S, and the two currents are oppositely directed in this. So, minus 2 plus S times, this is I1 of S, this is IFS, equals the total driving voltage in that first loop is in the direction of I1 is 10 plus S plus 2, 10 over S plus 2 rather. And as for the second equation is concerned, the total self loop impedance is 6 plus 2 plus S, 8 plus S times IFS, and the mutual impedance between loops 1 and 2 is S plus 2 as before. So, minus 2 plus S times I1 of S. The total EMF in the second loop in the direction of I is minus 2, because this voltage tries to drive a current in the opposite direction, therefore, this is minus 2. So, you have two algebraic equations involving I1 and I. You can solve for IFS through elimination of I1 through determinants or whatever method you are having, and you arrive at the expression for IFS as 20 upon S plus 4 divided by 9 times S plus 4, and this can be written further as 4S plus 20 divided by 9S times S plus 4. So, at this stage you make the partial fraction expansion for IFS in order to find IT. So, if you carry out the partial fraction expansion, it becomes 4 upon 9 divided by S, 5 upon 9 rather, upon 9 over S plus minus 1 by 9 S plus 4. So, in other words, I of t would be, once we have IFS, I of t would be 5 by 9 minus 1 by 9 e to the power of minus 4t. That is the expression for the current IT. So, let us see what we have done. We started with this circuit diagram, replace this by a transform diagram, and from the transform diagram you set up the algebraic equations for the pertaining to the transform diagram, and solve for the current IFS, the required variable, and find out the inverse Laplace transform. So, the steps that are involved would be to set up the transform diagram, In the transform diagram, you also with initial current sources, with initial condition sources, with initial conditions replaced by sources appropriately, either voltage source or current sources. From the transform diagram, you set up algebraic equations. Then get the Laplace transform of the response quantity whichever you are after, and then find the inverse Laplace transform response in time domain. For this you do the inverse Laplace transform. That then is the way in which we handle the network transient problems using the transform diagram. So, we avoid writing down the differential equations pertaining to this. By once you have the transform diagram, the solution runs on very similar and parallel lines to DC circuit analysis. The equations are written in the same fashion, except instead of the DC quantities, we write in terms of the functions of S. The currents and voltages are Laplace transform variables, and instead of pure resistances, we write in terms of functions of generalized impedances. This is also very similar to what we do in steady state AC circuit analysis. Again, instead of phasors, we use Laplace transforms here, and instead of impedances in terms of j omega, we write generalized impedances in terms of S. As a matter of fact, the writing down the equations is simpler than in the case of AC circuit analysis, because we avoid complex numbers. Even though these are complex expressions, we are only using S. S is a complex variable, but the coefficients of all the values of S and their higher powers are real coefficients. Therefore, we do not see the complex numbers explicitly in writing down these equations. So, this is the J terms which are strewn all over the place in the case of AC circuit analysis are avoided, or at least not seen here, and therefore, it proceeds in a very smooth fashion. The major difficulty, of course, is the finding out the inverse Laplace transform of this. If IFS happens to be a complicated rational function, then the partial fraction expansion and finding out the inverse Laplace transform is that much more complicated. But however, the procedure is straightforward. So, today in this lecture, we have we took for consideration the application of Laplace transforms to network transient problems. We saw there are two different approaches. One is to start from the differential equation. This is a very basic approach, a general approach, and we should always keep this at the back of our mind, because fundamentals are always very important. But then we would like to simplify the additional labor that is involved, because we may have to do this type of problems again and again in order to simplify the work. Instead of writing down the Laplace transformed versions of the differential equation, which turn out to be algebraic equations, we try to find out a shortcut method of writing down the algebraic equations. That then we develop the theme of the transform diagrams, which is an alternative representation of the circuit diagram, and from the transform diagram we straight away write the algebraic equations, the equations of performance of the network, and from that we get an expression in Laplace transform of the response quantities, and you find out the inverse Laplace transform to find out the response quantity in time domain. That constitutes the solution of the transient problem of a network. More about this in the next lecture.